Let's dive right into this explainer. Today, we're exploring the immense, unseen power of the electrical grid, and more importantly, the tiny, brilliant systems that keep the whole thing from destroying itself. Just imagine a massive, complex spiderweb of high voltage spanning across entire cities and continents. It takes some serious, highly specialized brains to keep that kind of raw energy flowing smoothly without catastrophic failures. Think about it. High voltage power lines are incredibly dangerous. We're talking about forces that literally have the power to instantly vaporize metal if things go sideways. So how do we handle it? Well, today we'll discover exactly how we tame these massive currents, using unsung heroes that act as the true brains of the grid, perfectly managing the flow of electricity so you can safely turn on your lights at home. Here's our agenda for today. First, we'll meet the grid guardians. Second, we're opening up the protection playbook. Third, we'll step inside the safe room. And fourth, we'll wrap up by translating danger to data. All right, let's kick things off with Section 1. Meet the grid guardians and look at the evolution of the grid's brain. It's honestly pretty wild to look at how this tech has evolved over the years. We started way back with traditional electromechanical relays. These literally used magnetic coils and actual moving mechanical parts to close contacts. In short, they were highly robust, but they were also incredibly slow to react and took up a huge amount of physical space. From there, we moved to analog static relays. These swapped out the moving parts for solid-state electronics like transistors, which gave us faster operation and lower power consumption. And finally, that brings us to the modern standard, numerical relays, built entirely on microprocessors.
Today's numerical standard is basically a high-tech Swiss Army knife. It takes raw analog signals from the grid and converts them into pure digital data. Because it's microprocessor-based, it processes complex algorithms and can perform multiple protection functions all at once. Plus, it communicates seamlessly with the grid's overarching master control system, SCADA, using the IEC 61850 communication standard.
Moving right along to Section 2, the protection playbook, specialized roles for specialized threats. So these digital brains don't just do one thing. They have highly specialized jobs, acting a lot like different defensive players in a massive playbook. Overcurrent relays trigger the moment current exceeds a preset limit. Distance relays actually use math, where Z equals V divided by I, to protect high-voltage transmission lines. Differential relays are hypersensitive. They compare entering versus leaving currents to protect transformers and generators. Directional relays keep a close eye out for specific fault current directions on parallel feeders. And one of my personal favorites is the Buchholz relay. It's a mechanical device that detects gas buildup from early-stage hidden faults bubbling up inside oil-filled transformers. Which brings us to Section 3, inside the safe room, separating the brain from the brawn. Look, these modern microprocessors, they are brilliant, but they are delicate. You absolutely cannot just bolt them onto a live, high-voltage power line. Physically, they're mounted on relay panels inside substation control rooms or integrated into switchgear cubicles. They're kept far, far away from the lethal energy of the actual transmission lines. They require a very strict physical and electrical buffer, living entirely in a secondary low-voltage control circuit. So how does the system actually react when something goes wrong? It follows a very precise fault-clearing sequence. First, sensor transformers out on the high-voltage busbar measure the activity. Second, those step-down signals are wired safely over to the relay in the control room. Third, if the relay detects a fault, it instantly closes its output contacts. And fourth, a completely separate DC battery supply energizes the circuit breaker's trip coil out in the yard. That flexes the mechanical muscle to snap the breaker open and instantly kill the dangerous circuit. All right, let's get into the math. Section 4, translating danger to data, unlocking the grid's secret language. Let's slow down for a second, because without these fundamental calculations, managing the grid would be literally impossible, not to mention incredibly dangerous. Relays simply cannot handle extreme primary voltages, like 220 kilovolts, or huge currents, like 2,000 amps. So instrument transformers step in to act as our translators. They use transformation ratios, stepping the massive, dangerous shouting of the grid down into a low-voltage whisper that the sensitive relays can actually read and process safely. So what do those whispers actually sound like? Well, these translators consistently convert the chaotic energy of the primary lines into neat, standardized secondary levels. For current transformers, or CTs, that safe whisper is standardized at either 1 amp or 5 amps. For potential transformers, or PTs, the secondary voltage is stepped down to 110 or 120 volts line to line. This feeds the relay perfectly digestible, safe data. Now, to figure out what's actually happening out on the live wire, the relay relies on the CT ratio, or CTR. The formula is beautifully straightforward. The CTR is just the rated primary current divided by the rated secondary current. To calculate the actual, real-world danger out on the line, you just take the relay's safe reading and multiply it by that CT ratio. Let's put this into practice. Say you've got a transmission line with a CT rated at 1,000 over 5 amps. That gives us a CTR of 200. Now, if the relay in the control room is comfortably and safely reading just 3.2 amps, it simply multiplies that 3.2 by the ratio of 200. Suddenly, the system realizes that a massive 640 amps are actually surging through the primary line right outside. Okay, let's flip over to the voltage side. It's the exact same logic, but here we use a potential transformer ratio, or PTR, to translate the voltage down. The PTR is the rated primary voltage divided by the rated secondary voltage. The actual line voltage is calculated by taking the relay's reading and multiplying it by that PTR. Let's run the numbers one more time. Imagine a substation with a PT rated for 132 kilovolts over 110 volts. That yields a PTR of 1200. Now, the relay measures a seemingly harmless 105 volts in the safe room. By multiplying that 105 volts by the ratio of 1200, the resulting calculation reveals something completely astonishing. Boom! 126,000 volts, or 126 kV. That perfectly safe low-voltage reading made inside the control room actually represents an unimaginably lethal force sitting right out on the primary busbar. And lastly, we can't forget about total power calculations. If a relay is calculating power, it's still using those scaled-down secondary values. So, to calculate the total actual system power, the system simply multiplies the relay's safe power reading by the overall multiplier of both the CT and PT ratios combined. That formula ties both of our translators together to give us a true, accurate picture of the grid's energy. It's honestly pretty wild to think about, right? The simple act of turning on a light in your house is protected by this incredibly intricate dance of hidden translators, safe rooms, and microprocessors constantly crunching this math in the background. They really are the unseen guardians of our modern world. Thanks for diving into this explainer with me. Keep exploring and never stop wondering about the incredible systems quietly running in the background of our everyday lives.